Telescopes are great, but when you put two telescopes and you separate them by any kind of distance, you can build a virtual telescope that is as big as the separation of those two telescopes. This is known as an interferometer, where you're combining the light from multiple instruments to be able to create a telescope that has a higher resolution than what you could do with any one single telescope. And there's plenty of examples of interferometers here on Earth, from the Event Horizon Telescope to the Very Large Telescope to other interferometers that maybe you haven't heard of. But we're really in the infancy of this technology, and it works fairly well on Earth, but where it's going to work really well is out in space. When you can put free floating telescopes out into orbit where they don't have to deal with the atmosphere and they can just point at two different objects, they can fly in formation and be able to gather images together to act like a telescope that is the size of the separation between those telescopes. There's a place that is stable. You don't have to worry about doing all of that free floating. You could just set down telescopes on the moon and they would be flying in formation just because they're sitting on the ground. So my guest today is Dr. Gerard van Belle. He is the director of science at the Lowell Observatory, and he is one of the people behind a whole series of interferometer missions. A very small interferometer that could fly on an upcoming CLPS mission to the moon and just test out what could you get with an interferometer on the moon. A medium-sized version that could allow us to start imaging the surfaces of other stars. A giant version that could fly with the Artemis missions, where astronauts would set up telescopes on the moon that would give us just a look into the cosmos like nothing we've ever seen before. So I think if you're at all interested in this technology of interferometers and where this technology is inevitably going, I think you're going to get a lot out of this interview. All right, enjoy the conversation with Dr. Gerard van Belle. Gerard, now, normally my audience, they're very technical. They totally understand everything about interferometers. I don't even need to explain them, but we're going to spend this entire episode going over the details of interferometers. So to make sure that everybody who's watching this is on a level playing field, can you give us sort of a basic understanding of what an interferometer is?
So a interferometer is a optical system in this context that makes images, and the idea with an interferometer is to make as high of a resolution image as you can possibly attain. So give your telescope the very maximum amount of zoom that you can to see something very, very minute far away. The little secret I always like to let people in on is that all telescopes are interferometers. You know, something like Hubble or James Webb, they all work because the light is collected by a single mirror and it's then concentrated to a point where you take a picture. But at that point, if the telescope is well aligned, then you get interference, and that actually makes for a nice point source. Hubble's a great example of where that was not done right, where the edges of the mirror were turned down by just a few microns, but you have to align things to, a thousandth of that, to nanometer tolerances. And that's why originally the Hubble images were fuzzy back in 1990. And they put in a little set of corrective optics that then, basically did the reverse of that little turn down on the big mirror. They basically turned it up on some small mirrors that they bounced off of and restored the interference condition and made it work.
So people with like Dobsonian telescopes, when they're out collimating them, they can say, I'm collimating my interferometer.
That's right. Yeah. And they are making things true to those kind of insane levels of tolerances. So for people that don't kind of have that off the top of their head, if you take a human hair and you measure across the human hair, that's about 100 microns. And you go down by a factor of 1,000 from that, and that is about 100 nanometers. And generally, optical telescopes, you need to align to about 10 nanometers to really get things in focus. And so all optical systems generally manage the distance that the light path goes through the system to about that level. And so Hubble, they didn't get it right, but they fixed it. Webb is another great example of where they have done this, but they did this with a big mirror that's made of small mirrors. But if you look at the overall shape of the small mirrors, both in terms of the small mirrors that make up the primary, and then they also have the secondary mirror, all of that aligns to those crazy levels of tolerance of 100 or a 10, or even in the case of Webb, much below 1 nanometer.
Right, right. But infrared is a little more forgiving for
That's right.
building your interferometer, right?
That's right.
Yeah. So that's great. But I think
Yeah.
most people, when they think about interferometers, they're thinking about essentially telescopes that are separated by some distance
Yeah.
to take advantage of the separation to give you that resolution. So explain sort of the pros and cons of how you set up an interferometer then.
So the pro is that you can actually take your pieces that make up the overall optical system and start to separate them very widely. The starting place is, again, Webb, where the separation between the little tiny pieces of telescope is very, very small. It's basically tessellated into a single mirror. But we play the game even further, and we basically take those pieces and pull them further and further and further apart, and have bigger and bigger gaps. And so you can synthesize a much, much larger telescope. Instead of, say, 6.5 meters in the case of JW, you can go to 100 meters. Or my colleagues on Mount Wilson with the Georgia State Char Array, those telescopes are 330 meters apart, all synthesizing a single big telescope. And you get to just crazy levels of resolution. Conventional telescopes are limited to an arcsecond, a few milliarcseconds, and with these sorts of devices, you can get down into, with certain measurements, kind of microarcsecond limits, and that's pretty neat.
And I think the example that people are very familiar with is the Event Horizon Telescope, where you've essentially built a
Yes,
telescope the size of planet Earth.
that's right. Yeah, and so there, um, basically whatever real estate they could find, they put a telescope on, and you get an extremely big telescope. The catch with an interferometer is that you start to have a lot of space between the actual glass where the light is just falling on dirt. And so you get resolution, you often sacrifice sensitivity. And so, particularly in the case of optical interferometers, you really are trying to look at things that are fairly bright. And there are a couple of reasons for that. Um, the With the optical interferometers, another thing to point out is that when you catch the light with individual telescopes, you actually, at those short wavelengths of light, you have to then very carefully take the light, bring it back together, mix it back up, and then you can snap the picture. In the case of longer wavelengths of light, like the Event Horizon telescope that you just brought up, you can actually, at individual telescopes, capture the light, detect the light, and then after the fact, inside of a computer, meld it back together. And so that's how you can get something as big as the size of planet Earth. And that's also why on something like the Char array or other optical arrays that are out there, they're all typically at the same location, spread wide ways across the landscape, but generally all then being able to transport the light to a central laboratory.
And so with, say, the Event Horizon Telescope, you've got, because it's radio waves, it is more forgiving. So you can literally just use an atomic clock to line up your wavefronts, while with an optical array, as you're saying, you're going to get them down to 10 nanometers. No atomic clock is going to get you what you need. So you're going to have to do it in real time to make sure that you've got everything nicely aligned.
Yeah,
So
it's kind of an analog versus digital comparison there. Yeah.
Now you mentioned bright objects. So give me a sense, like if you've got an optical interferometer, what is considered a bright object versus something that would be too faint for it to be, able to be picked up?
So the old rule of thumb that I always like to throw out there is basically anything you can walk outside and at night with a good sight see with your own two eyes. That for a long time has been the limit of optical interferometry.
Wow.
There has been pushes to dive in deeper than that. And the two major facilities, which include CHARA, but also include the very large telescope interferometer run by the European Southern Observatory down in Chile, they have been pushing on trying to get to bigger apertures and going fainter with those apertures. But with optical interferometry, there is a kind of a fundamental wall, which is the atmosphere above us. The atmosphere above us is this boiling, turbulent medium. It makes the stars twinkle. And it's a lot like trying to stare at a coin at the bottom of a swimming pool when your big old buddy has just jumped in the pool and it's all kind of dancing around. And because of that, the best we can do is to kind of roll with it, which is you at least try to freeze that turbulence out with very, very short exposures. And then you can kind of track and align things in real time if you're working within that exposure time. And that exposure time is about a millisecond. And so even when you get to bigger and bigger and bigger apertures, you're really fundamentally hitting this wall right away. And the other problem is that with you can build a big aperture. The Europeans with the VLTI have these. They have 1 and 1.8 meter telescopes that feed the back end. But they also have 4 8.2 meter telescopes that can feed the back end, and they do that off and on with kind of a silver bullet approach with the high value science. But the problem is when you get to a very large telescope, the atmosphere starts to kind of section itself up into these clumps of atmosphere spread over your big mirror. We call these things seeing cells, over which only over that little space is the light actually interferable and what we say coherent. And so you can put in systems to try and then flatten that out and make it so the clumps then appear to maybe just be one big clump. But it's a lot of very, very high-end servos and adaptive optics, and they're talking about laser guide stars now, and really cool stuff. And the Europeans are really excellent at throwing kind of industrial levels of might against these sorts of problems. But it's a nonlinear win. If you compensate for an 8.2 meter telescope, you still don't quite get 8.2 meters of return on that.
Right.
Yeah.
Right. So even with your adaptive optics system, because the telescopes are separated, you're getting not the same you're not getting the same atmosphere for each one of the scopes. And so you're having trouble bringing them together to build one image.
That's right. Yeah. So you do win some, and that's without question. And there are interesting special circumstances where you can win a lot, where if you have something that you're interested in and that's faint, but it happens to be near some kind of boring object that's bright, you can actually use that bright thing to do your housekeeping and drive your servos a little faster and make things a little more precise. And then, kind of giving it side eye, that's a good way of putting it, you can then look at this faint thing. And that's in fact what they did with, the Europeans did with the galactic center. They were able to do these very precise measurements of the center of our galaxy and see stars going around this black hole there, and seeing that they did not move in a Keplerian fashion. They actually had to sprinkle in general relativistic corrections to actually account for those motions. And, it ended up being part of the Nobel Prize win back in 2020, I think it was. So it's pretty cool.
Mm-hmm. Yeah, it's one of my favorite sort of stories, and I actually got a chance to interview Andre Getz about that work. And, just absolutely incredible. So I think for a lot of people, they wonder, couldn't just all of humanity, anyone with a telescope, all agree to go outside together, point all their telescopes at the same object, and work like a virtual interferometer? Couldn't we just add up all our telescopes and be a big team?
Yeah, the trick is being able to take that light and then put it together coherently. And probably after a fashion, we could do so incoherently and make a giant smeared image. But you're not going to get all that resolution baked into it if you're not joining things together at these nanometer tolerances that I was talking about. So, it's a great idea for harmony and such, but it doesn't actually work technically.
Right. So you would get the combined aperture of all of the telescopes, but also they would be suffering from varying levels of noise from the atmosphere. And so, but if you took them all to space, it would be pretty useful, pretty interesting.
So space gets you above the atmosphere. You do still need to mix things with this, with these nanometer tolerances being taken into account. And so this is why space has also been a tricky idea. So to put interferometers in space, one thing that the community has been talking about for some time is formation flying. Could we actually put telescope A next to telescope B, maybe have 100 meters between them, and do exactly what you're talking about, which is take the light, collect the light, relay it to some maybe third central spacecraft that does the mixing and then takes the picture. And there very much is desire to do this, and so much so that many of my colleagues have labeled this as inevitable. This is going to happen. The catch is that it's really hard to do, and that you have to control the path lengths to a nanometer. And there are actually ways to do that in terms of maybe you don't actually position the spacecraft to a nanometer. They could be wobbling around by many centimeters, and that's fine. But then inside of the spacecraft, you are very carefully moving mirrors that then you control to take out the centimeter level motion, and then you bring it down to nanometer level control. And that's in fact probably what's going to happen. But that's really hard.
Yeah, and you say inevitable, right? Like that there was like 20 years ago, the plans to build the terrestrial planet finder.
Yes.
And the SIM mission.
Yep.
And now people are talking about the LIFE mission, and still nobody is actually putting an interferometer in space. No one has a concrete plan for putting, and I would love to see like a near infrared or a far infrared interferometer, which sort of, I think, strikes that perfect balance between wavelength and the kinds of interesting things that you could see.
Yeah, I'm actually going to go visit the LIFE group Monday next, so 10 days from now or so, and visit Sasha Kwans is the main leader on that over in Zurich, and they are very interested in pushing that forward. LIFE is really kind of picking up the trail of breadcrumbs that was left behind by the terrestrial planet finder and by Darwin, but they're still talking about a 2045-ish launch date and trying to get there. And so they acknowledge that there's still a steep climb from a technology standpoint, particularly with regards to formation flying, that need to be developed. And so this is where I've come up with this idea for MoonLITE, an idea to put a very small interferometer into space and specifically onto the moon. And the idea there is to take that whole entire problem of formation flying and just throw it away. And the virtue there, and I was really inspired by, there's this great picture from the Apollo 12 mission, where you can see, who is it, Alan Bean standing next to Surveyor 3, which Apollo 12 landed within about 180 meters of Surveyor 3. And there's this picture, he's standing next to it, and I was looking at that and I'm realizing, Surveyor 3 and the descent stage of Apollo 12, they've stayed put relative to each other for the last 50 years for free, without even trying. And, they have achieved perfect formation flying just like that.
Right. To nanometer scale.
Yeah. And so part of that is then figuring out, is it actually nanometer scale? And the answer there is actually, it's about 20 nanometers when you actually do the math and research on the lunar seismic environment, which we know really, really well, again, from Apollo with all the seismometers and the tests that they did. Did you realize they brought grenades to the moon? I didn't know about this until recently, that for some of these tests of the active systems that they had with all these seismometers they brought on all the Apollo missions, they actually wanted to induce signal, and they had some grenades they would lob to actually do that. So I'm still trying to find more details about it.
I'm going to assign a story to one of my writers on this one. That's amazing.
Yeah, I do know that they also tested these systems by, Apollo 11 would put down a seismic system, and then when Apollo 12 was on its way there, its upper stage that they disconnected from before they would eventually go into orbit around the moon, they would actually aim that so that would impact the moon and again create a known signal to calibrate these things and measure the seismic signals. And so, anyway, that's a long ways and many rabbit holes of getting at the fact that it appears the surface of the moon is stable to about 20 nanometers for weeks sort of timescales, and then you get upsets with nearby micrometeorite hits that then kind of jar things. But that can be calibrated out and taken care of if you have some kind of array of telescopes on the moon. And so
give me a sense then of like, what kind of system are you proposing? How big of a telescope? What kind of separation and what kind of resolution?
So we tried to come up with something that was the absolute simplest interferometer you could think of. And this is something where you have a couple of very small apertures, so telescopes, literally 2 inches across, 50 millimeters across, for each of the input apertures. So tiny, very tiny. And two of them, because that's, again, your simplest interferometer. You would like to have, of course, a whole bunch of them, but for the very first one, just to get two, that's all you need. I've actually worked with a lot of interferometers over time that had just 2 input apertures. And so you take 2 apertures and you separate them. Along this axis, you don't get any resolution at all. But along the separation between the apertures, you get a lot of resolution. And so it's very good for measuring sizes of things that you maybe assume are round, like a star or a planet or that kind of thing. You can, if you have some prior knowledge that tells you that what you're looking at has spherical symmetry, then a size measurement gets you a long ways there. And so 2 apertures, and then the idea is to then take advantage of this opportunity to get to the surface of the moon with the CLPS landers. And so we have these commercial lunar payload services. That's been the first 2 missions already this year with the Astrobotic Peregrine, was that right? And then IM-1, which landed and tilted. That's kind of what landers do right now. And but there's going to be roughly 2 of those every year. And importantly, there are starting over in NASA Astrophysics, not lunar parts of NASA, but Astrophysics is starting to allow you to ask for a ride and fill up a payload bay on a CLPS lander. And so you get a very tight assignment. You get an assignment of about 50 kilograms. And then you also get 200 watts of power, and they provide comms. They actually make a lot of your housekeeping go away that you would normally have to bake into a CubeSat or a formation flyer or that kind of thing. And so our idea was something where you catch a ride on a CLPS lander, and the lander takes you to the surface of the moon. The lander provides a rover. That's another service that comes with this commercial lunar payload service. And the idea there was eliminate any kind of problems with the rover picking up your stuff by loading it beforehand. You preload the rover with one station, your outboard station, one of the 2-inch telescopes, before launch. And so that when you settle down onto the surface of the moon, the rover goes 100 meters away, sets down your outboard station, and you're deployed. That's it. You're done. Because the inboard station remains on the lander. Outboard station is 100 meters away. While you are setting this outboard station down, it's unreeling a fiber optic that goes back to the lander, and that's how the light gets transported. And so the outboard telescope has to get light into that fiber. But once you're into that fiber, you don't have to try and aim for the lander that you just came from to relay the beam over there. So the fiber optic solves that problem. And the fiber optic takes the light to the lander, where you have the experiment that puts the light back together, and you have your interferometer.
Does the altitude of the 2 telescopes being different, does that matter?
Nope. You can calibrate that out.
Right.
So in fact, when you set the outboard station down, it kind of needs to be like plus or minus a meter off that away. We have a kind of a general interest in being along an east-west line, but that's pretty generous with the constraints. We also tried to design the system so that if you have a CLPS lander that's going to go to an equatorial region, go to a polar region, somewhere between, we can deal with all that. The guidance we had from a CLPS program officer down at Johnson was to, levy as few requirements as possible on the lander, and that'll increase your odds of, if you get to that point, of catching a ride. And so we tried to make it as agnostic as possible where you went, and what the nature of the lander was.
So the mission goes well, the lander lands, the rover deploys your telescope. Congratulations, you've now built the largest optical telescope ever created by humanity, the largest aperture. What does this get you? 100-meter telescope with nothing in between.
Yeah.
But you at least get that baseline.
So it's not actually the largest one in the sense that 100 meters is still a little shy of, say, like what Chara does at 300 meters down
Oh, okay.
in
All right.
but it's still very big. And what you have created, and this is where the superlatives come in, is the most sensitive one. Even compared to these 8-meter apertures in Chile. And the reason for that is there's nothing in the way. There's, like you said, the only thing that limits your integration time is any kind of vibrations you brought along. Does this spacecraft vibrate? Does the lunar surface vibrate? But we think that we can snap a picture that lasts 300 seconds, 3,000 seconds, the better part of 10 minutes, better part of an hour. And here's the kicker. When you have an 8-meter aperture on the ground limited to 1 millisecond integrations, a 2-inch aperture surpasses that in its first second of integration. And then you keep on going to 300 seconds. And so we expect the limiting magnitude that in astronomical terms isn't like 12th or 13th magnitude, which is about what you hit from the ground, but like closer to 17, maybe 18. And so that's about a factor of 100, 1,000 in faintness of looking at things.
And so now you're looking at things that you couldn't see with your eye.
Yeah. Oh, yeah. And now you're looking at things that, even with these giant telescopes from the ground, you couldn't see. And so we actually, as a science team, when we were developing this concept, ran into this problem where we're like, whoa, what do we do with this? What are all the applications? And it was kind of an interesting challenge to be like, we were trying to dream up crazy stuff to do with this. And so there's some bread and butter stuff that lends itself to it. From the ground, you measure the sizes of stars a lot. This helps you calibrate their temperature scales. If you know how bright something is and how big it is on the sky, you put that together, it tells you its temperature. That kind of runs out of steam for the smallest, faintest stars because they're just too faint. You can't measure their sizes. And with this thing, we immediately realized, we can actually just keep on going way down the main sequence into things below the star limit, into measuring the sizes of brown dwarfs. And this is very interesting for the theorists in that they are building these models of these brown dwarf stars, and it is a challenge to figure out how convection works on the inside of it. How does energy transport through these stars? And if you could at least just tell me your size of that star, that starts to pin down a lot of the questions about, how it's put together on the inside. And so just a simple size measurement gets you a long ways. And so we figured that was good. And then that's the really nearby stuff in a kind of a galactic sense. And then we just started moving outwards. And it's like, okay, well, what's next? Well, the young stars that are getting born with planets getting born around them, we've seen these really incredible images coming out of ALMA, the submillimeter telescope in Chile, where we see these kind of bullseye-looking things where you have a disk with a bright central spot, that's the protostar, but then you have these lanes carved out of the disk around these stars. And that's because we expect that that's where the planet formation is taking place. But if you look at the spatial scales of these things we're looking at, it's all like, 20 AU, 40 AU, 50 AU. It's all the cold planet regions where you're having Uranus and Neptune and Jupiter being born. And what you really want to do is you want to work inside the central pixel there and see what's going on with how the terrestrial planets are being formed. And so we could actually start to poke at that with this because we have a lot more resolution than ALMA, despite being, ALMA goes across many, many kilometers, but, we're only 100 meters across, but we're operating at much shorter wavelengths. And so we get much more resolution. And we'll be able to start to get a window into that terrestrial planet regime and see what's happening there. And then you march further out. There was a person on our team who was suggesting what you can do if you look at the cores of active nearby galaxies. So we're going from, say, 500 light years away to now 10 million light years away. And there's this whole question about what's going on, what's the plumbing of the active galactic nuclei when you have black holes gobbling up material around them, or maybe binary black holes orbiting them. There's a whole subculture of trying to figure out what the final parsec problem is inside of active galactic nuclei. And so that was fun. And the craziest idea, which I think is the most fun, was saved for last, which is trying to characterize the nature of space-time foam. So get this. At cosmological distances, the stuff that's really far away, quasars, way, way out there, you have this thing that's a very, very bright, very point-like object that emits light, and this light travels across the vast distances of the universe itself before it gets to you. Well, what is the universe itself, especially at the microscopic level, at the Planck scale, 10 to the minus 35 meters? People think it's this grainy, bubbly space-time foam. And when you take light and you propagate it through a chunky medium, you will take a plane wavefront of light and it'll start to get corrugated. It'll start to get clumpy. And what this manifests itself as, if you're looking at a quasar that's very, very far away and expect it to be just this sharp point of light, it'll actually maybe appear to not be a sharp point of light. It might actually be a little fuzzy. And if you see that this fuzziness increases as you go to more and more distant quasars, that potentially gives you a handle on measuring the very structure of space-time. What is the Planck length in the universe? And so that one's a super speculative measurement, but it looks like it's possible we can at least provide some constraints on that, if not make an outright measurement of that kind of thing. And so, so we're trying to dream up these crazy ideas for this thing because it provides you with the sensitivity to see those distant quasars or these terrestrial planet-forming regions that was not possible from the ground. We even baked into the overall observing program about 20% just open time because we finally came to the conclusion that we couldn't come up with enough crazy ideas for this thing. And we would, if we were to fly, we would then solicit from the community, what do you want to do? And, can you come up with some kind of fun new way to use this thing? And so we were very excited about the overall prospects for this.
When I think about a 50 millimeter lens, two 50 millimeter lenses, I mean, that's the size of the opening on my water bottle.
Yeah.
Right. That's really, really small. And yet if you separate two of those by 100 meters, these are the kinds of things that you start to get.
Yep.
Now, did you think about if you go farther? What if you separate them by a kilometer? What if you go 10 kilometers? What if you go put one on one side of the moon and one on the other side of the moon? What's the sweet spot, do you think?
So I think the sweet spot is about a kilometer, maybe 10 kilometers. You do have this need at those wavelengths of light to take the signal and bring it together to a central recombination point. And, if you're on one side of the moon and the other side of the moon, that's a lot of piping, a lot of light fiber. But, you could easily think of setting up a spool of a kilometer, 10 kilometers of light fiber to do that. And so I think that's pretty plausible. Certainly in the radio, where you can detect and then mix after the fact, much greater distances are possible. And they're actually talking a lot about that for radio interferometers on the far side of the moon to take care of that to take advantage of that natural shielding of the moon. In fact, those are actual funded flying missions for at least initial test stations on that. There's one called LucyLIGHT and LucyNIGHT that will try this technique out. And so that's very exciting that something's actually flying rather than, in a proposal stage like ours is at. But I think the nice thing about MoonLITE is that it's really not intended to be a project. It's intended to be, the camel's nose under the edge of the tent in terms of a whole family of projects where we show, look, the stable surface of the moon is really useful for astronomy. We should just build everything like this and take advantage of this increased angular resolution. Because whenever you have increased angular resolution when you're looking at things, you have discoveries. I love the idea of how we achieved this in a roundabout way with, putting a telescope on a small but very fast spacecraft called New Horizons, and we went and took pictures of Pluto. There we got very, very high angular resolution, not from a fancy telescope, but from a lot of patience. where we waited 10 years to get the pictures back. And then we had this beautiful little heart from Pluto. And it's like, Pluto's great. But yeah, that anytime you increase your spatial resolution, you make discoveries. That's been throughout the history of astronomy. When Galileo first built the telescope that he had and looked at Jupiter, boom, Galilean satellites. He immediately discovers these 4 moons of Jupiter, and it like completely upends the cosmology of the time. And so anytime we're going to be able to push on that, I think that's going to make more discoveries, and this is the way to do it.
Yeah. Okay. So it's 2030, and you have successfully gotten a mission on the CLPS mission, and maybe even the Artemis astronauts are walking around your telescope carefully. What comes next? I mean, what would be a feasible, billion-dollar version of MoonLITE?
So I've actually been part of a study team with a group led by Ken Carpenter at Goddard, talking about a Artemis deployed stellar imager. And the general idea there is about that class of mission, about $1 billion, and to set down on the order of 16, maybe 30 1-meter telescopes and link them all together and do stellar surface imaging at very short wavelengths. So take advantage of the fact that you can go down well bluer than what we can do from the Earth's surface, because at about 300 nanometers, the atmosphere is opaque. And so we would want to go all the way down to like 1216 angstroms, 121 nanometers, where you can look at the surfaces of stars in Lyman alpha, this very active line of hydrogen, and you can basically measure the flares that are coming off and the turbulent boiling medium of these stars. That's going to give us a lot of insights on the magnetic connection of the surfaces of those stars to the corona above them and those sorts of things. And so that's very exciting and very interesting to think about. I actually see an intermediate ground between, your really tiny experiment class mission and, gargantuan facility class thing like that, which we ironically have called EASY. That's Artemis-enabled stellar imager, which we pronounce as EASY, which it is not. And so, but I think in the middle, there's a whole class of NASA missions, the mid-X style missions, the medium class explorers. Those are kind of about a $300 million cost cap, where we can send 2 or 3, probably 3 telescopes of moderate size, maybe 10 inches across, starting to get into where astronomers ironically flip from inches to meters in how they measure telescopes. But yeah, maybe a quarter of a meter across. And yeah, 3 apertures where we can use that to very precisely measure the positions of stars and see their reflex motion due to planets going around them. Effectively do the mission that SIM was going to do before the SIM, the Space Interferometry mission, got canceled, and measure the masses of nearby planets, terrestrial mass planets. That's seen as a highly motivated possible mission because of NASA wanting to build this Habitable Worlds Explorer for the 2040 timeframe. HabWorlds really needs the masses of the planets it's going to look at. When you get a spectra from a planet and you're trying to see, is there ozone there? Are there is there a chlorophyll edge? Is there some kind of sign of life? Turning spectra into signal, you usually need to put into that modeling the mass of the planet to help peel that whole thing apart. And you cannot get the masses any other way. You really, really want the astrometry that gets you the masses, this reflex motion, and that needs interferometry.
And so, ESA's Cheops mission is characterizing planets that have been seen via the transit method. Yeah. And it's just come back around and doing tons of observations. The upcoming aerial mission from ESA is going to characterize transiting planets and measure their atmospheres. But you're suggesting something that would be using, say, the radial velocity method to measure the masses of these planets, but also astrometry, like what Gaia is doing. So would it both be able to measure the kind of the side to side motion of the star as well as the back and forth?
So this would actually just be the side to side in the plane of the sky. That's so just the
Okay.
astrometry. Radio velocity is really getting to exquisite levels of performance just here from the ground. Um, in the end, it'll be interesting. My colleague right across the hall works on this, Joe Lama. He and many astronomers around the world are working on trying to push on that radio velocity technique to get it finer and finer, but it really looks like they're kind of hitting a wall at about 1 meter per second. And that is a level of precision for detecting planets that does not quite get you to Earth mass planets, about a factor of 10 greater than Earth mass. And they're really smart. And I think they'll be able to push that down to more, to maybe 30 centimeters per second. But that's still not quite all the way there. And the problem with the radio velocity technique is, since it's just along our line of sight, it has a ambiguity as far as the inclination of the orbit. For some of them where it transits, for example, like you called out, you know the inclination, but for the ones that don't transit, you're not sure what that is. And I think for the objects in our immediate solar neighborhood that are going to be the primary objects for habitable worlds to look at, they're not going to be aligned that way. You get a chance alignment by having a lot of targets, and that means you have to increase the volume of what you're looking at. And habitable worlds is really going to want to look at stuff that's just on our doorstep, 10 parsecs away, 20 parsecs away.
So would you be characterizing known exoplanets in, say, the Gaia data, or would you be just doing your own version of Gaia where you're watching a whole bunch of stars and trying to measure the motions of the stars with astrometry?
A bit of both. And we would take a page out of the book from the radio velocity people, which is the best place to find planets is where you've found planets, which is to say, there's, it seems obvious with some of the findings that they've come across, which is when you find some planets or a planet around a given host star, keep on looking because you'll probably find more. And so I think there would probably be, you would want to maybe, bias your sample intentionally a bit to look at places where you have something like a Jupiter in a distant orbit, and then see if you can detect, undetected small mass planets closer in. Planetary system architecture that's a little closer to, say, what we have in our own solar system. The comparison to Gaia is a good one in the sense that the single measurement accuracy of Gaia is on the order of 50 to 100 microarcseconds, so a very small number. But that's really your defining number on how small of a planet you can find. Gaia averages a whole bunch of those down to get general characteristics of the star itself, but in so doing, any planetary signal kind of gets averaged out. And so we want to design something that would be in this $300 million mission class that could get down to 1/10 of a microarcsecond, principally because that's the number that is attached to an Earth going around a sun-like star in an Earth-like distance, and so that's what you got to do.
And so you would have a mission, like a bespoke mission that would have its own lander and its own rover. It would land on the moon and then deploy these telescopes. What kind of how big of a baseline would you be looking at, and how big of telescopes?
So there would be on the order of the individual telescopes be on the order of 1/4 of a meter, so
Yep, right.
roughly 10 inches, and the distance would be about a couple hundred meters. And what's defined by that is you could try to go further. You're probably principally limited by the spool of fiber you're reeling out behind it. You could also look at that point maybe just a free space relay where you just have a mirror that relays the light. Interesting problem on the moon. The horizon distance is short. You start to drop below the horizon really quick because it's a small ball, not a big ball like the Earth. And so at about 1 kilometer, you got stuff that's starting to drop below the horizon. So you need to put it up on a tower. And so there's all those complications. But the more limiting complication is at about 200 meters. You're trying to look at this source star that is the host of the planets you're hoping to look for, and you are starting to over-resolve it. You're starting to have so much resolution that it's kind of hard to get a handle to hold on to the star and kind of measure its position, because you want to look at the star and you want to see its photocenter kind of wobble around as you have some unseen planet pulling on it. And at 200 meters, you're starting to make the signal of the star a bit of a mess. And this is kind of an ironic problem with interferometers, is you often get into the case of over resolving things. This is always one of those hidden things when people say, well, why don't you make an interferometer with 100 meter or with 100 kilometer baseline? You could actually probably come up with the technology that would get the light all put together, but the signal smears so badly out on things at that point that it actually is not a lot of use in doing that. So yeah, 200 meters seems to be about the sweet spot for that application.
And would you be looking at individual targets, or would you be doing something more wide field like Gaia and observing a swath of the sky at a time and then trying to detect the motions of individual stars in that field?
So again, in between, this would be specifically designed to do two things at once, where you look at your host star of interest, and then you would look at some kind of reference star that would be like a background giant, where you know it's a long, long ways away, maybe a kiloparsec away. And that way you can measure the angle between those two things very accurately with this kind of system. And then if the nearby star has a planet going around it, you would basically then see it wobble back and forth. And then this would, your reference star in the background would be locked down because it's just so distant. Any kind of signal, if it had, itself a planet going around it, is undetectable. But yeah, you need, it's a lot like with your kitchen scale. You need to be able to press zero and zero the thing out. And that's what the background star does. It gives you your fiducial.
Mm-hmm, mm-hmm. Okay. So we've talked about like the prototype version that sounds very feasible, and I hope it flies. We've talked about the sort of mid-level one that's a few hundred million. We've talked about the potential of $1 billion one that the Artemis astronauts can take out. And I think that's special because, many of them are going to be amateur astronomers, and the fact that they can go out and just like see the telescope and tinker with it and look where it's looking, like that's going to seem really meaningful. But I want to know about the secret one, the ridiculous one, the one that you have on your file system that's marked, bonkers idea that no one's ever going to take you seriously, but in your heart, that this would really work. And, I'm going to open up the checkbook. Money is no object. What is this sort of perfect lunar interferometer in your mind?
The perfect one?
Mm-hmm.
Well, the very long range science goal that I would love to see done is not detecting an extrasolar planet, but actually mapping its surface. And I want to see continents. I want to see oceans. I want to see changes seasonal with vegetation coming and going as you go from winter to summer. That's really hard because then you need just extreme resolution, and you also then need extreme sensitivity as well, because you're starting to get to the point where you need a certain amount of light, not just from the planet, but from every little patch of pixel that you're putting onto the planet. And so you need, 10, 20, 100 meter class individual telescopes. And you need baselines that are, on the order of tens of kilometers. That is probably the place where you then maybe circle back and think, at that point, maybe you really do want to have free flyers in formation in orbit somewhere rather than on the surface of the moon. It's just such a behemoth. And a kind of a pet idea of mine that I've had for a long time that is actually not hidden in my file folder here, but actually published, is the idea of, how big of a telescope can we build when we really push on it, and where do you put it? And so on the ground, we've been going to bigger and bigger and bigger telescopes. And the Europeans are building a 39-meter aperture down in Chile next to, a few miles away from the VLTI that they currently have. So this thing that has, more than 100 feet across of glass. And it's amazing. It's going to be huge. But does it make sense if we ever want to do a 100-meter single telescope? Where does it make sense to do that? And one of the things that I've always been fascinated with is, if you can wave your magic wand, if somebody's given you a blank check, what would happen if you could start manufacturing mirrors in space? and actually building optical quality mirrors up there. And it's interesting. You immediately realize some interesting advantages, which is it doesn't have to survive launch. And so it doesn't have to fit inside of a payload shroud. And so right now, biggest payload shrouds really limit how big, say, JW was, even with JW being kind of origami folded up. But if you could have a mirror that is 10 meters across or 20 meters across in a single go, you don't have to worry about fitting it inside the payload shroud. You also don't have to worry about it shattering on launch because it's already up there. And so you could envision making it really gossamer, a few millimeters thick, let's say, or a few centimeters thick, something that would never survive launch. And you could end up having a very large mirror if you had something printing like that. That actually, pulling on that thread led me to work with Made in Space, which is now part of Redwire. We actually have had a really productive collaboration over a number of years talking about what things you can do with manufacturing, either that or more mundane things like just support structures in space. And I think there's a real future there where, we're going to see a lot more industry in space, both on the surface of the moon, also in orbit. And that eventually is going to lead to that. I think that's kind of, again, inevitable, to use that word.
And so maybe was it the Archinaut? So maybe you got this Archinaut or something like that that's spitting out these trusses and building the framework, and then you're launching a flat, you're launching a tube filled with 30 mirrors, and then they get attached like web, and then you build up this giant spherical or parabolic mirror in space with all of those components. Or maybe they can actually 3D print with the resolution that's required, that you can just make the thing. And I like that idea where, if it's a certain kind of mirror shape, you could just keep adding to the outer edge of it, and it just gets bigger and bigger and bigger. And then after a while, you put one beside it, and then, just keep attaching them. Right.
Yeah.
And so you could, as long as you know where they are associated with each other, the system gets better and better over time.
Yeah. Yeah. There are ways to do that. I've actually seen Archinaut in its little room. Sadly, is not slated for launch anymore right now. But we were adapting the Archinaut technology for beams that would hold outboard stations of a 2-element interferometer. And that was a very simple demonstration flight we were looking at maybe doing as a free flyer before we latched on to the idea of, it may just be simpler to put it on the surface of the moon, because all of, the boom goes away, the whole bus goes away, because you have all that provided by the CLPS lander. It basically was a way of just stripping the entire experiment out. Everything else goes away, and it becomes much simpler from our standpoint. So, but yeah, I think there's a lot of exciting things where you could think of mirrors. If you could manufacture just spherical segments, there are classes of telescope that are made up of a spherical primary where every little segment is the same as every other little segment. And you could start with something small and then tessellate into something bigger and bigger and bigger.
Yeah. Well, if I could pitch a name, the Inevitable Space Telescope, I think sounds sounds appropriate.
There's a whole XKCD about that.
Yeah, I know.
Upcoming telescope names. Yeah.
Okay, so I want to also, you have been responsible for bogging down my entire writing team for the better part of a month now.
Excellent.
Yeah. And that's because you, and I don't know if this was planned, you released a whole bunch of papers all at the same time, and they all were the kinds of stuff that I'm exactly interested in. Mm-hmm. And I kept spotting these papers and assigning them off to writers. And I'm like, wait a minute, your name just keeps, I keep seeing Gerard's name in each one of these papers. So the other one that I want to talk about is the Big Fringe Telescope. And this is to build one here on Earth. So let's talk about the Big Fringe. What is that?
So the BFT, so much cheekily named, and a riff on BFR, is something where we try to embrace the yuck, where there are limitations of doing stuff here on Earth, and with ground-based interferometers, groups have taken interesting tacks on what they want to try to accomplish. And so the Char array and the VLTI people, they have pushed very hard on trying to get to more sensitive capabilities for their instruments, and rightfully so. It brings all kinds of new science when you can see fainter things and try and detect things that couldn't be seen before. But this BFT, the Big Fringe Telescope, the idea was to not go that direction, but go in a direction of more resolution and more the ability to pick out more detail on something you're looking at. And a surprising science case that has been overlooked is the bright stars. So the things that literally you can walk outside and see with your own two eyes, and even the brighter ones of those, where you've got a lot of signal and you can sample it with a lot of telescopes and try and make a more complicated image. With an interferometer, as you add more telescopes, your ability to get more pixels increases. And so the idea here is, say the VLTI uses 4 telescopes at a time, the CHAR array uses 6, but we were aiming for something more like 16. And there are certainly variations on this where we even think about like 24. And so make as many of those as possible, but then kind of collide it with this idea of let's make it affordable and easy to build. And so this is really taking advantage of the last 30 years of technology development in astronomy. So both CHARA and the VLTI, they were originally conceived of and initially built in the kind of late 90s, early 90s. And so all of that technology is a marvel, but it's pretty dated. And so, for example, the guys at CHARA, this is actually a whole adventure story you should look at too. When they wanted 1 meter telescopes, they had to build their own. And nowadays I can cut a check to PlaneWave, and my friend Rick Hedrick over at PlaneWave will send me a bunch of 1 meters in a few months. These guys at CHARA, they were clever in their own way. They were like, the Iron Curtain just fell. Let's go see if Russian manufacturers can build us mirrors. And so they're cutting checks to the Lomo Glassworks in St. Petersburg. And it was a really kind of fly-by-night thing, but they have these beautiful primaries from St. Petersburg that went into their telescopes. And but they had to build these things and design these things all themselves. And so nowadays, I can just cut a check and cut a shortcut and have something show up that is my telescope. I've also kind of designed into it not a 1 meter aperture, but a 0.5 meter aperture, in part because this adaptive optics, we were talking a little bit about that earlier on, about how the atmosphere is a real problem of having clumps of atmosphere over the face of your mirror. At the 0.5 meter scale, your telescope is actually usually grabbing only a single clump of atmosphere, a single seeing cell. And so if you have fast tip tilt rather than this exotic adaptive deformable mirror, and you have a very simple way to account for the atmosphere being crappy. And so the idea is, every station that you have collecting light for you and sending it back to the lab is very simple and off the shelf and cheap, because you're buying a lot of them. And if you design it that way, it makes it so it on the periphery of where you're grabbing the light is very cheap, and then you bring it together in such a way that the transport of the light to the back end is cheap, because nowadays with 30 years of technology, we can do this with fibers, with optical fibers again. Everything prior from CHARA and GSU, let's say, uses these pipes, some of which in some cases are evacuated. You suck all the air out, and that's a pain and a lot of giant scale plumbing and alignment. And, if you just have a fiber that's lying on the ground or actually buried, it's much simpler. And so there's a lot of these ideas that are baked into it to try and make it affordable and off the shelf. And if it's off the shelf, that means stuff shows up on a predictable schedule, and it's easy to build. A lot of these projects have gone on for decades in terms of their building. And, I've got enough gray hair I'm hiding underneath my hair color that I want something done quickly, because I'm, I don't want to have to wait 20 years for something, because I'll be on retirement by then. So, yeah.
Yeah. I love the practicality. I think the wisdom part of those gray hairs is you saying not what would be amazing, because everyone has proposals for, you go to the AGU or the AAS and you watch people talking about ideas that would be amazing. And then you think about practically how many missions actually launch, what's the process, and so on. You're looking at decades. But I think your insight here is like, what is people would just go like, why don't we already have 7 of these? Because it sounds so easy. And you're like, I know. So how many telescopes and how big of an aperture would you be looking to build with the Big Fringe Telescope?
So this would be 16 telescopes in a big ring, and that's spread across the landscape here. One of the things that's very nice about northern Arizona, where I'm at here, is that we have large, big, flat, open spaces and places to put that have very good seeing, very good astronomical sky quality. And it's funny because with a telescope that size, but input, if it's 2.5 kilometers across, but input by these rather small telescope, it would actually be pretty hard to spot because it's just going to be like a shed over here, a shed over there. There will be a big central laboratory where everything gets put together. But we would have just a big building that the only thing that really reveal that it's there. And then we would stare at the bright stars. And the idea here is to work from a known list of targets where we have a very specific science case where it's like, we are going to do this science case and maybe other stuff will be possible, but this is the focus and we will design it to this one thing to do really well. And the idea here again is the stars that are probably going to get looked at by habitable worlds, the ones that probably have planets. We won't be able to see the planets with the BFT, but we'll be able to see the star really, really well. And you want to characterize those stars. I mean, the mantra in astronomy right now is if you want to know thy planet, you have to know thy star. And it's because so often you detect the planet by what it does to the star. You only see the star wiggle or wobble, and that tells you the planet is there. And then if you find the planet there, if you want to know how hot it is, or is it getting irradiated by UV flux, you want to do that by looking at the star. And so we want to do surface mapping of these stars with, say, 10 by 10 or even 30 by 30 pixels across the face of the star. And by so doing, we'll be able to see spots moving across the surface of the star like we can with our sun. That tells you a lot about the magnetic dynamo inside the star. It tells you a lot about the rotation rate of the star. Is the rotation rate differential? Do the spots at high latitudes move differently than spots at low latitudes? Is there a difference in how bright the edge of the star is relative to the center of the star? This is a phenomenon called limb darkening, actually, that we see on our sun. It tells you a lot about the upper structure of the temperature in the star. And these are all things you get with a picture. And we would want to do that.
And I think people would be surprised to know, like, even with the biggest telescopes on Earth, I think, we have images of the sun, the surface of the sun. And I think Betelgeuse, a couple of pixels of Betelgeuse.
Yep.
And that's it.
Yep.
We don't have, everything else is 1 pixel.
Yep. And so we have surface images only from interferometers for a wider variety of stars. And those surface images are pretty simple right now because of the limited number of telescopes at the current facilities.
Yeah.
But the really kicker science case here that I'm probably am burying the lead here is there are those cases. These are known cases. We have about 30 of these that we've identified where we could look at it with the BFT, and you would not only just see the disk of the star, but you would see the planets that transit the disk of the star. So there's about 30 of these objects where we know there's a planet that goes between the surface of this host star and our line of sight. And you can actually see the disk of the planet, and you resolve the disk of the planet into more than just 1 pixel. That's wild to see the shadow of another world resolved as it transits its host. I think that's going to be really cool.
Yeah, that's really cool. Gerard, what are you obsessed with right now?
I could be accused of being obsessed with interferometry for the last 30 years of my career. It's a useful technique, and it's a fun challenge always to try and get it to work. I see it as a real tool to tell us things about the nature of the universe. I think ultimately the broad goal in astronomy is something that I share, which is to find life elsewhere and to find not just planets, but have some robust indication that there's some life there, even microbial life, because I think that'll have profound philosophical implications on how we view ourselves. And and by no means am I trying to, am I in pursuit of this goal because I think it's going to have us look at ourselves and diminish ourselves. I think it actually will give us insight on how special life is in the universe and how we need to take care of it. And that's really exciting to literally be building tools that move in that direction.
Yeah, it's interesting to me how many people I talk to who will go on and on about whatever very detailed astronomy coronagraph project they're working on. And then in the end, when I ask this question, it comes back to, are we alone in the universe? Like this is it's a weird thing to be at this point in history where we don't know the answer to this question. And yet it is a scientific question and there is an answer, and it really is just a technology problem for us to get there to the point that we've got, like, they haven't come to us. So now we have to find them. And we can answer this question within a couple of decades or not find an answer. And that's weird too. Back to Arthur C. Clarke's sort of,
when I talk to some of my colleagues, I think is it Heidi Hamill or Deborah Fisher, they talk about the Habitable Worlds Observatory that wants to be built in, the next 20 years. And they rightfully point out that, it is providing an answer in such a way that is a civilization defining question. If we can come up with the answer to that is a milepost in history that will last the ages.
Yeah, I remember when LUVOIR was the original telescope and now it's being shifted to the Habitable Worlds Observatory. And I was talking to one of the project directors behind that. And he says, if we get to a 20-meter telescope that is capable of resolving these worlds, we can scan worlds out to a radius around us that we can sort of numerically predict how many civilizations there are in the universe, how many planets there are with life in the universe. And if we find none within the capability range of LUVOIR or the Habitable Worlds, then we could say with a fairly high level of confidence that there is no life elsewhere in the universe. But if we do find a world here and a world there and a world there, then we have a number. We know about approximately how populated the universe is with life. And both answers would be equally terrifying.
Yeah, that's right. That's right.
Yeah.
And we live in a very special time in that, in the last, say, 10, 15 years, we had the flight of the Kepler spacecraft and, the specifics are here and there, but the general discovery of Kepler that the general tendency of stars is to have planets. Being able to make that statement with certainty is completely revolutionized how we look at the universe around us. And from that one flight, and habitable worlds can potentially then notch it up to that next level of then life.
Well, Gerard, thank you so much for your time. I look forward to all of these missions, including the inevitable Space Telescope coming online, and definitely will continue following. Take a bit of a break to let my writers work on something else, but then feel free to come back at it and produce more papers. Thank you so much.
Thank you, Fraser.
That was a mind-blowing interview with Dr. Gerard Van Belle. I'm going to be walking around for the rest of the day in a stupor, pondering the implications of what he expressed to me today. And I hope you feel the same way. Now, I'm going to give you some more thoughts and ideas, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Barry Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbox, BiderSwap.io, Stephen Krasaki, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Like many of you, I have been just fascinated by the idea of interferometers for a long time. This idea, this magic that you could take two telescopes, separate them, and now suddenly they work like a telescope with the equivalent of the baseline between your various apertures, and that there are lots of downsides, and yet there are very special science cases where you get these upsides. And Specifically, I've been really interested in the potential of putting these things in space. Gerard called it inevitable. I think that's like a really good way to go. It is the perfect place for an interferometer to fly. And we'll get there. We'll get there. At some point, there will be a mission that either puts one on the moon or puts one into space itself. And we will truly go to that next level of being able to answer that fundamental question that we talked about right at the end there. Are we alone in the universe? This is a scientific question. We're building the tools to be able to find out the answer. And in our lifetimes, we will either know the answer or know that we seem to be alone. And either one is terrifying, but also interesting. All right, we'll see you next time.